Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good webinar on multi-robot coordination in complex environments, organized by the ITU. This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping to unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. Without further ado, I would like to introduce our moderator today. His name is Herbert Tanner, and he's professor at the University of Delaware. Bert, welcome, and the floor is all yours.
Thank you, Guillem. A warm welcome to you all from me as well, joining us today for this exciting discussion on collective robotics and multi-agent systems. As Guillem said, my name is Bert Tanner, a professor in mechanical engineering at the University of Delaware. I'm also the director of the Center of Autonomous and Robotic Systems there, and I have the distinct pleasure to have here with me for this panel discussion four exceptional individuals and esteemed colleagues who have all left their mark in the scientific study of multi-robot systems. I'm going to start introducing Maria Gini, a College of Engineering distinguished professor in the Department of Computer Science and Engineering at the University of Minnesota. And Maria works on decision-making for autonomous multi-agent systems. Rachid Alami, a senior scientist at CNRS and academic chair on cognitive and interactive robotics at the Artificial and Natural Intelligence Toulouse Institute, who has been working on multi-robot coordination, planning, and human-robot interaction. Annie, Hsieh, who is an associate professor in the Department of Mechanical Engineering and Applied Sciences at the University of Pennsylvania and deputy director of the GRASP laboratory. Annie has been designing algorithms for estimation, control, and planning for multi-agent systems. And Amanda Prorok, professor in the Department of Computer Science and Technology at Cambridge University, and a fellow at Pembroke College, who has been doing some of the most prominent and exciting work on resilient multi-agent systems. So welcome to you all. We're going to start with 10-minute presentations by each one of the panelists. I'm going to save questions at the end of all the presentations. And after that, we're going to follow up with a panel discussion before we open the floor to questions from the audience, both on the presentations and on the panel discussion that we will have. So with that, the first presentation is going to be by Annie, followed by Amanda, Maria, and I'm sorry. The sequence of the presentations would be first Amanda, then Maria, then Rachid, and finally we're going to close with Annie. Amanda, you're on.
Fantastic. Can you see my screen full screen?
Everything looks great.
Fantastic. Well, hello to you all. Delighted to be speaking here today. So today I'm going to be talking about learning to communicate in multi-robot systems. So I'd like to start with this little video here where we can see that there is a lot about collective intelligence and collective decision-making that is really beautiful. Here, this beauty is exemplified by the smoothness and elegance of emerging motion patterns that you can see in the swarm of starlings. And although we know that this behavior is based purely on local interactions, the higher order goal is invisible to us, and hence the magic of these systems. So collective intelligence, turns out, can also be put into practice. And I'm showing you here a couple of the very successful recent case studies where we've been deploying collective intelligence into the real world. So you're familiar with logistics, warehouse automation, transport, and agriculture. But the kind of automation we can see multi-robot teams doing has also shown to be very promising out in the wild for environmental monitoring and surveillance and construction, and also out in the space. The key point here is that whether it's through simple coordination or through more sophisticated forms of collaboration, these systems perform better when there are several robots working together. And so what I do in my research and the things that we're interested in understanding is how to get these robots to work together. So why is coordination actually a hard problem? Well, it turns out that we need to figure out how we want the robots to interact and what and with whom they need to communicate. So why is it a hard problem? Well, first of all, coordinated decision-making is actually hard. It's hard because many solutions are intractable. Second of all, as we decentralize the solutions that we're developing, we need to figure out what robots need to communicate to one another, when and how they're going to do it. And finally, even if we can develop and devise solutions that can solve the first two pillars, we then transition to the real world, and the real world is full of unexpected occurrences. So we need to be robust. We need to be robust to delays, faults, failures in our system, and our solutions need to incorporate this. So we can tackle these problems with either classical, conventional, first principle solutions, or we can actually take a data-driven approach. And the hope by doing this is that we can generalize across problem scales and problem types. And so what I want to give you an insight into today in these few minutes is a couple of ideas that we're having, or the community is having, around how to deploy data-driven approaches to these very hard multi-robot problems. So it turns out that agent-to-agent relationships can actually be represented as graphs. And we can exploit this underlying structure to facilitate the learning problem. And so what this boils down to is that we have a neural network that allows the robots to encode what they're seeing locally and devise a messaging strategy that allows them to cleverly interact with one another so that the receiving robot can incorporate these encoded messages to make smart decisions about what it has to do in order to solve a downstream task. So we've gone about doing this, and in some recent work, we actually showed that we can learn to communicate, to coordinate, to solve a really hard coordination problem. So one of the hardest coordination problems we actually know is one called multi-agent pathfinding. In computer science, this problem belongs to the class of NP-hard algorithms. And what we showed is that we can actually automatically synthesize local communication and decision-making policies to solve this very hard coordination problem. And what's remarkable here is that our solution is fully decentralized, and hence there is no computational downside as we scale the system to hundreds or even thousands of robots. Of course, we then are faced with the problem of, well, we have these solutions that we've built in simulation, but what we really care about is transitioning these solutions to the real world. And in robotics and computer science, we call this problem the simulation to reality gap. And we've been going about solving this problem with various ideas and approaches. And I'm going to show you a couple here. So on the left-hand side, we've been thinking about learning in mixed reality, where we actually have one robot in a real system running in the real world, but it's interacting with other robots in a simulated environment, jointly in mixed reality, so that as the robot is learning, it's not breaking other robots, it's safely interacting with them because they are operating in a virtual world, yet it still is receiving the signals and learning from these signals so that it can improve its collective decision-making policies. In the center, we've been developing methods built on graph neural networks and studying how communication in the real world impacts their performance. And we've been able to show that as communication degrades in the real world, our policies that have been trained purely in simulation are actually very robust to these communication degradations in the real world. And finally, we've been looking into how to get robots to learn to communicate when the robots really need to rely on the communication amongst partners in the real world. So in that third problem, what we've done is we've studied the problem of how to navigate a blind robot towards a target that is completely out of sight and have it be guided by a visual sensor network. So the robot here is relying completely on these sensors that are distributed in an environment whereby the sensors are telling the robot in which direction it has to move in order for it to reach a target, in this case, a green box, in an environment where the robot cannot see the target from the get-go. And the remarkable thing in this scenario is that the robot isn't positioned and the sensors are not positioned either. So they are learning from their visual surroundings and from what they're communicating to one another in order to find a way to guide the robot in the most promising direction for it to find its ultimate target, its ultimate goal. And this is all really remarkable because it's plug and play. We don't need to calibrate the systems. We don't need to position anything. It's all done through data-driven communication strategies. And here you can see a video where you can see the individual visual fields of the individual sensors and how the robot eventually navigates to the target and reaches the target, which was originally out of sight. And the final thing I want to talk about is the fact that we're often thinking about the robots as the problem and the robots that need to be fixed and the robots that need to get better algorithms. But we've actually in my lab been putting the problem on its head. And we've said, well, sometimes the robots and their algorithms can't be improved, but what we can improve is the environment that they're operating in. And so we've been thinking about how to formalize this problem by considering the environment as the variable that we can control and deploying robots with fixed policies into these environments that are now malleable. And so what we studied is this example where robots have these navigation policies and they want to reach their goals, but there are some scenarios where the environment is very hostile and doesn't lend itself well to the underlying task. So as you can see here in this movie, it's very difficult for the robots to find a way around all these obstacles in order to reach their goals. And so we devised a strategy which allows the environment to be configured or reconfigured as a function of the robot algorithms. And you can see here that by making very minor and subtle improvements to the environment, the robots are actually able to achieve their goals much more successfully and smoothly and efficiently. So let's think a little bit more about the environment as part of our problem too. And with this, I'd like to summarize with a couple of key points and messages that I hope you will take home with you from this short snapshot of some of the things we're thinking about. So the frontier for me lies with novel neural network architectures that are really allowing us to facilitate the learning of these decentralized policies and that provide scalability at very little performance cost. And we've seen that these policies are very promising because they can cross the simulation to reality gap in an elegant way. There are a lot of opportunities that I'm incredibly excited about. So the holy grail really is to learn to solve computationally intractable problems with solutions that actually scale. I'm really excited about the idea of co-optimizing the environment. We need to broaden our perspective on what it is that we're trying to solve and how we're trying to solve it. And finally, I think we should think more about how to provide resilience to unforeseen disruptions through collective intelligence. There are a number of challenges that the community is working really hard on. The first being interpretability. So we have these robots driving with data-driven policies, but we do need to think a little bit about how we're devising these policies and whether or not the humans that interact with these systems actually understand what is happening under the hood. We need to think about the efficiency of devising these solutions as we progress with data-driven approaches and how to transfer them smoothly into reality. And finally, we need to think about how to provide guarantees and certifications, especially when these systems operate in safety critical or shared human-robot environments. With this, I'd like to thank you for your attention. I'd like to thank my team and thank my sponsors, and I look very much forward to the Q&A session at the end of this. Thank you.
Thank you, Amanda. Fascinating. And I particularly liked and was intrigued by the idea of thinking the environment not as a static set of parameters, but something that could be played around with. So with that, I would like us to transition to Maria's presentation.
Okay, so what I like to do, talk a little bit, if we have lots of robots, not just one, not just 10, maybe 1,000 or 10,000, what could we do? How can we interact with such large number of robots? And just the key ideas I'm going to go over. If I have just one robot, it's relatively easy to control. There's been a lot of work has been done. But you have multiple robots, they can be more useful because they can work in parallel, but they're more difficult to control. And we have to make sure that whatever programs we develop, they have to be able to scale to the number of robots, be robust to failures, like Amanda was mentioning earlier. So the question that comes up is, how should the robots coordinate with each other? Do we want a centralized system, a distributed system, each individual robot doing whatever they want? And I just toss in an issue here, which I'll come back later. How can you detect when you have a group of robots? If one of the robots is not going to do his share of the work, maybe it's been programmed by somebody else. So we're going to start very briefly. I'm showing a few pictures again, simple robots. We can think about social robots, companions. And again, I've shown a few pictures here. They're very wonderful. They do good things. But again, they're simpler. Now, let's take about many robots. What I'm showing here is the first real example of a large set of robots. There are 100 robots. It's a DARPA project a number of years ago. And you see those robots all line up. Now, the robots at that time didn't really do much. So, they were just programmed with a robot in front, pulling, in a sense, virtually all the other robots to follow. The other figure here is from Harvard, is the kilobots. 1,000 robots. Each of them is very small, moves very, very slowly, doesn't do much. So most of the work for many years has been done really engineering exactly each of the robots for a specific situation. So they're not really generalizable. What I'm looking at now, suppose now I have many, many, many robots, and this is a little more modern. Now, the inspiration that people often use is from ants. You can see, ants move around, run things. Now, if I show you a little bit of this simulation, you can see, I mean, this is a simulation of 10,000 robots kind of moving around and picking up food. But how are they going to be coordinated? How are they going to work together so we accomplish what we want? And what do we want? I'm not going to spend much time. I have a few pictures here of some examples. Some of these robots are deployed, like Amazon. Some others are more futuristic, like the drone to deliver, your medicine or your newspaper, maybe each morning. So the question now is, if I have many robots, how should I interact? So we start very, very simply taking a quick look at, I moved too fast. Let me go back. If I have a few robots, like in this case, there are 3 robots that meet in a corridor, the question is, how are those robots going to interact with each other? They don't know, they're not really programmed to know exactly what's going to happen. Think about people, right? When we move in a corridor, we move around. And so again, I'm showing here these robots are thinking very, very quickly, figure out what to do, and then have to decide in real time how to move to avoid running into the other robot that is coming to them. And once they decide to do, they move and they kind of try to be not too aggressive. So you see this robot kind of moves around and gives space to the other one. And so there's a lot of issues here that how we control them. But if we have really very large number of robots, this is simulation only. This is a short video from a RoboCup search and rescue simulator. All the things you see moving around are robots. The red ones are fire trucks, the blue ones are police cars, and the white ones are ambulances. All the green dots that you see that are getting dark, those are people that have to be rescued. And what you see here in the corner of the city, you see that the city started burning. And this is a simple map of Paris, and Paris is a river, so there are only a few bridges to cross the river. So again, the question here is, how can the robots save the city as much as possible? And what I'm going to show here very quickly is if the robots are working individually, so each fire truck decides where to go and what to do, there's no coordination, explicit coordination among them, you see slowly that the map has a lot of areas that are becoming brown, black, they're all burned out. And the robots are doing their job, but they're not coordinating with each other. So by the end, most of the city is burned, and that's not really what we want. Now, same situation, same agents, but now they do some coordination with each other, exchanging some message, do some communication. And now you see that even though, yes, they still have the fires are spreading because, they're hard to control. But if you keep track, because all the red dots, which are the fire trucks, are all kind of attacking the same fire from multiple sides, you see that the damage to the city is much more reduced. So the point here is having many robots that work on their own is fine, but if they can do coordination, will be better. And I'm showing here, talking here very briefly about some work we've done, in which now we're thinking about not thousands of robots, but maybe, tens or few robots. And suppose they have to do a surveillance task. And what I've been interested in figuring out how the robots can decide which task to do, where the tasks have precedence constraints and have temporal constraints. Like you have to watch a room in a time window, and you have to watch, check critical areas first. And how do we do it? And here I just try to give you a little bit of glimpse of an algorithm, potential algorithm. There are many other methods of doing the same thing. And the algorithms we've been using are based on auctions, like when you go on eBay and you submit the bid. So it's the same idea. And the idea here is very simple. So each robot builds its own schedule, and we can kind of see the schedule as a collection of circles connected and keeping track of time. Now, time is an important component here. And then the robot decide, okay, I've already committed to do this kind of things. And now I have this other task. Can I do it? How much more will it cost? And the cost will be the time it will take, because the robot has to go to a new place and figure out the best place in the schedule to put this. Once each robot has done this, they submit the bids to the auctioneer. Now, the computation here is done on each robot, so it's done in parallel, right? That's where we gain a lot. And then the auctioneer select the best bid and continue. Now you can say, is this going to work? Very simple example I'm showing here. This is done with the vehicle routing, which is in a sense is the same kind of problems. You have trucks that have to go to different locations and have, again, temporal constraints. So the example you see here on the top part is our algorithm. And you see, without being told, we end up that each robot picks up a vehicle, picks up an area, and then does all the tasks that close by. And the reason is, once you pick up an area, all the tasks that are close by are very cheap, right? Because there's very small movements you have to do. The other algorithms we try don't do the same thing, so they don't work as well. So at this point, I'm kind of ready to wrap up, and some areas to think about. We can think about the robots have to be controlled. So we need somebody to decide to control. We can do, teleoperation in some cases, but really more interested in programming. And, we have to tell the robots what to do. Now, of course, I'm not even touched the problem here. Amanda mentioned it earlier, is robots can also learn. So I'm not talking about learning, I'm talking about simply decision-making and how to get distributed decision-making. When the number of robots is limited, again, we can do like our algorithm auctions. So, we can have each robot deciding what to do and kind of plan things carefully. But if we have thousands of robots, it's not clear that these methods, like even our auction methods or some other methods, will really work. And doing the coordination is much more complicated. Again, if you want to make sure only one robot goes to pick up an object, you need coordination. And if you have 1,000 of robots, if you've done simulation with 15,000 robots, it's not clear what's the right ways of doing things. And the last point that I want to make that I mentioned earlier, again, I didn't get into any details here, but it's something to think about. We can typically we program the robots to be nice to each other, to cooperate, to be helpful to each other, not to try to run into other robots, but there's always a possibility. And we have to think about it as scientists. Suppose that I have a robot either was put in by a competitor, by enemy, or somebody just want to have fun and try to break into my system. So how can the robots kind of recognize, if I have programmed them, that, well, maybe this robot doesn't really do the right things. Maybe he's not our friend. Maybe we should try to isolate or do something else. And again, those are all open problems and we can talk about later. Thanks a lot for your attention. And I'm looking forward again to the discussion we're going to have. Thank you.
Beautiful, Maria. Thank you. And I appreciate the fact that you brought into and you showcase to the audience, our audience, the stark difference that coordination can bring to the performance and efficiency of a task. Great. So we're moving on to Rachid. Rachid, now is your chance to amaze us all.
Yeah. Thank you. Can you see my slides now? Yeah.
Yes, great.
Okay, thank you. Thank you very much. So I'm very glad to be here with you and to share this moment with you and discuss with you. So I'm going to present here some ideas and I would say dreams about the future concerning teams of humans and robots. So my topic of research today is essentially human-robot interaction, or more precisely, human-robot collaboration, in the sense that we are looking with my colleagues also it's a topic in the community, interesting in the community, of this issues link of developing cognitive and interactive abilities for a robot to allow it to collaborate with humans and to be pertinent, transparent, legible, and acceptable while performing its task. the applications, as you can imagine, are the service or assistant robot of tomorrow, and also the teammate robot in the factory or in the field, for example. And so, as I said, my talk here is to share with you. I worked for years on multi-robot cooperation and multi-robot coordination. Also, that was a topic that I like very much also. And I think it is time to think of how to mix both. And I think what Maria just said just before me is already going towards this direction. And so let's make a kind of, in 2000 XY in public space, X is superior to 2. You have a place when you have cameras all around, you have Wi-Fi, network, and this is a kind of public space. And this space, you have a group of service robots performing their tasks, their duties. You also have some cleaning robots, for example, a team of cleaning robots also working and performing their activity in this place. You have, of course, humans there. You have also perhaps some semi-autonomous wheelchairs transporting people, and you have some companion robots or assistive robots coming with their master in this place. And you have humans here. And the issue is how all this could coexist and could do something pertinent and useful for the humans, and do not simply space their time inefficiently, I would say, colliding or in conflict. I have worked on a number of projects of human-robot interaction where, for example, here you have a robot that is doing a task mission, a task guide mission, guiding people in an airport, an assistant robot at home for fetch and carry applications, for example, or a service robot for info and entertainment in a public space, or also a teammate robot in a factory sharing the with the co-worker. And this pushes somehow to think about this very well-known and very old photo of the workers of the building the skyscraper. And in the future, we'll have this. You'll have teams of humans and robots working together and to achieve a global mission, like building a skyscraper or a base or similar issues. And this takes us to the need for every robot, really the need to be endowed with capacity to interact and achieve and interact with humans, but also capacity to interact with other robots. And why? Because this is, of course, for efficiency, but also for robustness, compliance, and coordination. Also, it could be interesting that these robots could possibly take benefit of the others, and also, why not, help or facilitate the activity of the others, even if they are not from the same company or the same team. And so this takes us to think about this in the future, two types of interactions somehow, what we call domain and task dependent, and what we call generic interaction abilities. So domain and task dependent could be all these abilities for a team of robots to perform or a task cooperatively, like cleaning, for example. It's specific task, or surveillance mission, specific with specific constraints and specific ways, capacities to perform. But this could also happen if you have a team of human and robots. Okay, so there are humans, there are robots, but they are on the same team and they are working together for a given task. So it's really domain and task dependent. And then you could have generic interaction abilities that could help also. For example, when a robot from a company encounters a robot from another company performing another task, okay? A cleaning robot encountering, for example, a surveillance robot. It would be good if they have some interaction abilities, generic interaction abilities, at least for sharing space, for instance. Also, it could be necessary, of course, for a robot when it encounters a passerby, so not a person to which it is not a teammate, but simply a passerby, or to take benefit of general purposes that are provided in the infrastructure, for example. So we could imagine that all these capabilities I would say, used in the framework of one given interacted robot. Now you have humans. Humans and robots have different roles, and this has to be taken into account, of course, in this systems. And what is important here is to build robots that are able to effectively conduct cooperation with humans. So we are working on this. I will not go into details, but essentially, and what is interesting here is that we can share, I would say, and take inspiration from a large bunch of I would say of research, from multi-agent and dialogue to development psychology to people working in the issues of joint action between humans. And joint action is a key aspect, by the way, because it shows clearly how we humans are able to collaborate and to share a task and to perform a task collaboratively. And what are the signals? What are the duties? What are the tools that we are using to perform such kind of very fine collaboration that we are able to do? And would like to have the robot being able to do the same in interaction with humans and also in interactions with other robots. So, and all these questions have been also asked by before me in the first talk. These issues are key: what to do, who will do, where, when, and how at various levels. But with the specific issue that robots should avoid to be incongruous, I would say. Why? Because it is very important to understand that human and robot are not equal. The human is not restricted to the task at hand. Humans do not have at any time, do not need at any time to stay blocked in the task. They have latitude to change focus, to disengage, to change goal. And the robot should adapt to this. Robot should adapt to this, to the, I would say, latitude and freedom to the human. And at the same time, the robot should be legible, acceptable, and comfortable in its behavior. And so this is what we call in my team human-aware task and motion planning, essentially, where we use essentially cost estimation of plans to choose the best possible plan to perform an action. I think I will be a little late here, so I will go out of this, simply mentioning that what is important to see here in this slide is that you have human and robot in multimodal interaction, sharing space, sharing task, and sharing decisions. And we have the robot not only a reasoning of the task, reasoning and observing the human, but also reasoning on the fact that it is observed by the human, and also trying to estimate and predict the human mental state and the human knowledge about the task and the environment in order to be pertinent in its plans and in its behavior. And in order to do this, we are engaged into, we're not working only on roboticists, but as a multidisciplinary collaborative endeavor with psychologists, philosophers, and roboticists on these issues. And here I am mentioning a place where you could find a presentation from all these people with slides and from this different point of views. And I'm concluding here. Thank you very much.
Thank you, Rachid. And it was very exciting to bring the human into this picture. It's a topic very close to my heart, and we're going to have the opportunity to talk a little bit more about it in the ensuing discussion.
Thank you.
We're going to move on to Annie now, and some might say that I saved the best for last. So Annie, it's your turn now.
Bert, the pressure that you're giving me. So thank you so much for this opportunity to be part of this panel with these wonderful colleagues, such inspiring talks. So I'm very honored to be here today to tell you about some of the work that my group does and sort of the context that we think about multi-robot systems. So my group mostly tackles the scientific and technological challenges centered around using teams or collectives of robots for environmental monitoring applications. And so For example, right, we want to improve the data that we collect, or our data collection efforts in the ocean, to help us better understand and predict how the ocean changes over time. So we know that the ocean, in fact, drives climate weather patterns across the globe, and we're currently experiencing, right, sort of the effects of climate change. So what I'm showing you in the top left-hand side, that is a satellite image of Typhoon Hinnamnor. So this was, it actually went from a tropical storm, to a category 3 or 4 storm in a very short period of time. We also have seen a lot more larger and harder to fight wildfires, both in the United States as well as in Europe. The video in the middle is showing this was the flooding that happened in Philadelphia, right where I live, 2 years ago due to Hurricane Ida. And so in addition to climate change and other geopolitical effects around the world, right, what we're seeing is this mass migration of population. They're traversing sort of very long distances across very, very challenging terrain. And so all of this, right, all of these are challenges that we're facing in our time. And even if, sort of without, in the absence of these challenges, right, we rely on our natural world to power our economic activities. And so any kind of accidents, right, can cause not just a very sort of horrible environmental impact, but it can also have a very negative sort of local economic impact as well. And so my argument is the fact that robot teams are not only crucial, but necessary tool in our attempts to better monitor, manage, and protect these large-scale environments in a sustainable, equitable, and resilient manner. So despite the importance of our natural environment, much of it remains somewhat unexplored. And our understandings of the complexities of their dynamics is shallow at best. Part of this reason is because these are very, very large environments. They have significant dynamics. These are all sort of effects that make it very difficult for you to deploy a robot within these settings. And so oftentimes what we see is we use large remotely operated vehicles like the Hercules, which is shown in the panel sort of on your left-hand side on top. And then the boat, the orange boat, that is actually Cell Drone. This is a remotely operated vehicle. These are large. They're mostly remotely operated, if not actually human piloted. And because they're extremely expensive, oftentimes we can't really deploy large numbers of them. But for us to actually understand the spatial and temporal variations of our environments, we actually need to be able to sample across both space and time simultaneously. And so oceanographers use, sort of in the middle panels, the top one is an Argos float, and the bottom one are Lagrangian drifters. These are passive vehicles that get deployed. And so if you're in a static environment, that's where the sensors stay. But if you're in the ocean, they sort of follow the currents, take them wherever the currents are flowing. So for you to be able to really be able to adapt and actively collect data, you actually need to have real robots. And so what I'm showing you sort of on the left-hand side, these are two examples of robots. The top one is a sort of unmanned autonomous vehicle that is flying through a forest, trying to figure out how the trees are doing. And then the bottom is a Slocum glider, which operates underwater. And so one thing to note is that this is, these are actually sort of platforms that are being deployed for different types of uses and are actually now operating in the real world. But of course, so the issue of using large teams of robots, right, it's not just an issue of cost. There's also challenges to contend with when we're sort of deploying these autonomous systems in these highly dynamic environments. For one, if you're thinking about operating aerial vehicles, or if you're thinking about operating marine vehicles, the coupling between the environmental dynamics and the vehicle dynamics makes the controls problem very, very difficult. And this is especially hard when you're dealing with small vehicles that have very limited power budgets. However, right, for every challenge, there's an opportunity. And so it is possible that we can, in fact, leverage and harness these environmental forces to be able to extend a vehicle's navigation capabilities. So the figure, hopefully, that I'm going to show you down there, so these are a family of energy optimal paths that leverages ocean currents around the Philippines archipelago for a marine vehicle. But for us to be able to leverage these environmental forces in planning and control, we actually need to model relevant environmental features. These environments, right, they're trying to figure out what the right features to track is often a very challenging perception problem, okay? But even if we had this ability, right, sort of, for large scale environments, we actually, we'd have to be able to sample across both space and time. And this is exactly the type of task that a team of robots is going to be extremely well suited for, okay? But of course, this is sort of previous speakers have alluded to, in a lot of these natural environments, communication is actually very, very challenging. You either don't have line of sight or you're operating within a medium where the only technology you can rely on is going to be very low bandwidth and very lossy. And so any kind of multi-robot strategy, really has to work with very limited network connectivity. And so in my group, we think about developing large-scale, smart, adaptable environmental monitoring networks that can consist of various static and mobile sensing platforms. These heterogeneous sensing networks, right, would include things like satellite, surface, underwater, sort of in the air, or passive, as well as mobile observational platforms. And the idea is really to use this smart, adaptable monitoring network to be able to achieve continuous and persistent sampling of our environment, where multi-resolution data can be fused into a consistent picture of the environmental dynamics. These environmental models can then be incorporated into our autonomous vehicle deployment strategies and enable the network to adapt their sensing locations in an on-demand fashion to further improve the quality of the data collected. So the result is effectively a virtuous cycle where high quality data leads to higher quality models, will lead to more effective sampling strategies. But since these environments are large, right, and instrumenting these can be very costly, the strategy is not about blanketing, right, our environments with sensors and with robots, but instead to think about what we can achieve with limited sensing resources, and also really thinking about how do we do this when we're severely constrained in terms of communication. And so really the philosophy or the approach is really about making the most of what we have. This is in terms of sensing resources, but also in terms of the data that we can collect, okay? And so in fact, within my group, we sort of deal with all parts of this cycle. We think about how to plan where to send our different sensing resources. So the video in the top left, this was actually work with Amanda. And so this is thinking about when we have a heterogeneous team, each with different sensing capabilities, where do we send them? How do we leverage environmental forces to be able to create communication networks that can, whose communication links can come in and out? And so this is shown by the video at the bottom left, where you're seeing, so there's these blue robots that have information, be able to propagate that information over time to robots in red, where they don't have communication with all the time. And so this, in fact, is work that we did with Bert's group. In addition, we think about how do we fuse, right, sort of data collected from disparate sensors. So what you're seeing, this is a video of an experiment where we disperse dye into a fluid. The middle panel in the top, that black and white picture, is actually the robot reconstructing that field through their onboard sensing data. And you see the robots moving around in the video on the upper right-hand side. And so this idea is that they're constantly adapting their sampling locations and then fusing that new information into the model description, okay? We also think about how we leverage data and also leverage this sort of enormous corpus of physical knowledge that we have of these very complex environmental processes, and use both, our physical understanding of what's going on in the environment, and then complement that with the data that we're collecting in order to build more predictive and more powerful models. And at the end, I'm going to stop here. So we think about how do we design more novel vehicles that can better harness the environmental forces in order for them to go about collecting their data, traversing this environment, and essentially stay within that environment for a more prolonged period of time. And so this, I'm just showing two platforms. We have an origami ball that can change its shape, and through that shape change, be able to better interact with the environmental dynamics. The bottom is an array of what we call these mod boats. These are very low low-cost single motor floaters, and so they have ability to sort of push themselves against the flow, but they're not really, they're fundamentally underpowered. Okay, so I'm here just going to conclude because this is the work that I just presented. This is from my group. Feel free to visit our website for more information. But so this is really a team effort, and it really requires collaboration between various engineers, scientists, and sort of as well as policymakers. So here I'm going to stop and thank everyone, and I look forward to the discussion.
Thank you, Annie. And thank you especially for bringing to the forefront the idea that we can use robots to tackle some of the enormous challenges that we face in terms of climate change and the human response to that challenge. So a quick look to see if we have questions on our presentations from the audience, and we're going to move right into our panel discussion. Okay, just to remind everyone, we could still receive questions while we're discussing, and we're going to have also some time at the very end for any questions that might come up. So with that, I'd like to thank you again all for your wonderful presentations, and I'm going to start with Annie and ask her what she would think that the biggest opportunities are in multi-robot systems technology as they deploy in complex and challenging environments. And we can take the marine robotics arena as one example of extreme environments for robots. Maybe you can elaborate a little bit on that, Annie?
Yeah, so I think right now we're sort of really at a stage where the opportunities are increasing. Okay, it's a very challenging environment to work in. So if we think about where we need to collect data, right? So if we think about the ocean, it's really a three-medium problem. You have the ocean itself, which is water. You have that interface between the ocean and the atmosphere, so that's air on top. And then you have the interface between the ocean and the suds or the ground. And so that's, this sort of, within that, regime, you're crossing all kinds of Reynolds numbers, but you're also sort of, the complexity of that fluid also changes significantly. And yet we actually need data across that entire spectrum in order for us to really be able to understand what's going on. So at the fluid and atmosphere, at the fluid air interface, right? So this is a great opportunity because we actually don't have a lot of sensing information. This is a very challenging interface to be operating at, and yet this is a very crucial sort of interface because that is actually the interface that drives the heat exchange between the ocean and the atmosphere. And this is sort of what causes, hurricanes and typhoons to intensify. And this is also what causes, sort of these kinds of El Nino and El Nino patterns, right? Weather patterns. And so we're at this stage right now where we actually have a lot of low-cost sensors. They really have to be sort of weatherized, but it's really also how do we sort of build better systems that allows us to be able to deploy them in these sort of environments, or these areas that we really have not thought very much about.
Okay, great. So you mentioned about challenges here and building better systems, more capable robots. What do we actually need? What is missing right now from our community, our robotics community as a whole, to be able to build these robots, to make these, to be able to harness their potential and exploit these opportunities?
So I think we have a lot of building capabilities, right? So if you're mostly working on land, we actually do have a lot of sensor platforms. I think the challenge, of course, is really operating these small-scale, power-constrained systems into these very complex environments where you're expected to do real-time perception, real-time communication, and then real-time planning and control, right? And so this is sort of this, and you got to move within this environment. And these are all sort of very power-hungry necessities, and to be able to. And so some of this is not, I don't want to sort of just couch this as a battery problem, but this is this combination, this is really a systems problem, right? How can we not just think about the components, the design of the components themselves, but thinking about designing the whole system, that we can be very clever about leveraging how these vehicles are actually interacting with that environment, and where can we do better optimization to prolong the operational lifespans of these vehicles.
Great, Annie. I love that you framed it as a co-design system level problem rather than just an individual kind of niche area. So thanks again. I'm going to move on to Amanda, and I have some questions specifically about resiliency in multi-robot systems. So Amanda, you have been among the most prominent researchers on the topic of multi-robot resiliency, which I definitely agree is a critical feature and property of any large-scale system that aspires to be deployed in the real world. How do you understand robot resiliency? Could you explain it to us, give us a definition? What do you think still keeps us from developing robotic systems that are truly resilient?
So I think the key thing about resiliency, and this is what makes it so hard, is it is supposed to capture the unthinkable events. And I'd like to juxtapose it with the term robustness, which is, I would argue, otherwise well studied, where classically in robustness, we would assume that even though sometimes we're trying to model very bad events, we still have some sort of model of what the unforeseeable could be, right? And then we devise those models, and then we have our control strategies that function around those models, or those essentially models of what we think could happen. But the problem with resilience is we're looking at things that we really don't have models for because they are out of distribution, right? So think black swan events. And what makes it very difficult to deal with that is, as we don't have a model, we don't know what we're trying to be resilient against. And I think this sounds like a hopeless problem, but the key idea here is thinking of resilience from a multi-robot perspective, actually. Because what we can do is we can actually think of these systems as collectives. And collectives have this unique property that they might afford redundancy, they might afford complementarity, they might afford diversity. And hence you're looking at communities that are actually not operating at optimality at any given one point in time because they have redundant resources or latent or dormant capabilities, but then something unthinkable actually happens. And those capabilities then come to the rise because the collective knows how to reorganize itself to the new situation, to answer for this unthinkable event that happened in this new situation for which we did not have a model a priori. So this is really how I see the difference between classical approaches to being robust versus thinking of resilience as much more of a broader kind of systems-wide problem and also property. And there are quite a couple of properties that I think are uniquely attributable to resilience that don't necessarily fit well to what we consider classically as robustness. So this idea of not operating at optimality is perhaps foreign to many systems. So just satisficing is an interesting idea in itself. You're functional, you're solving a task, but you're not doing it particularly well. You're basically surviving. But because you're basically surviving, you're holding back some skills and some capabilities that you're going to bring forward that allow you to survive over longer durations of time. And that's kind of the trade-off. And that's kind of the way I think we should start thinking about our systems as we deploy them. I think this does require quite a bit of rethinking from the way that we traditionally approach problems, because we're mathematicians or control engineers or roboticists or computer scientists, and we're always trying to optimize some objective. And so we need to take a step back and think about, well, perhaps it's sustainability that I care about. Perhaps it's really flexibility and adaptability that I care about. And then we need to rethink the way we're actually formulating our problems in the first place. And And then kind of to round it off, I really do think that multi-agent perspectives and multi-robot perspectives and perspectives from collective intelligence do bring a very important aspect and an important element to addressing this item of resilience.
Great. And Amanda, I love that you stressed the difference between robustness and resiliency, and you urged us all to move, or at least start thinking about outside the realm of optimality, because optimality can be fragile. But I also want to touch upon an issue that you brought up in your presentation, and this is probably a good time for us to discuss, because the last decade can be characterized as the decade of deep learning. Impressive breakthroughs, widespread adoption, explosive number of applications. How do you think deep learning, can offer, and what is its place in multi-robot setting that other alternative, more analytical approaches would not be able to give?
Yeah, it segues really nicely into that topic. So I think there are two major fronts where deep learning or machine learning or data-driven approaches can really propel us forwards. And the first one actually relates directly to resilience. So we can think about generating data examples that are difficult, that are adversarial. We can think about producing, kind of simulating or emulating the hard situations we think our robots might be situated in, and presenting those situations in the form of data to the robots so that they can learn how to deal with those unthinkable events a priori. And why a data-driven approach is so promising for this is because it's hard to develop a model for the unthinkable, but we can create narratives around the unthinkable, and we can create simulations that simulate what we think the unthinkable might look like. It's a complex thing to do, but we can generate these things. And that's where I really think that we can bring data-driven approaches back into the story as approaches that do promise this little bit of additional, that gives an edge over conventional approaches. And the other front, I think, is very interesting from the multi-robot or multi-agent perspective, is this idea that we can achieve tractable solutions to otherwise very hard problems. So the idea here is really to think about, for example, cloning optimal behaviors that we know are optimal, and we know how to solve for very small problem instances for which we know how to deal with the computational issues. And then we clone those behaviors, we tell a machine to learn or to copy them, and deploy the resulting policies onto much, much larger systems, which then again through conventional methods couldn't be solved because they're intractable. But this cloned policy knows how to copy that ideal or idealistic behavior. And then the magic of it is that it normally would scale, right? So the challenge, of course, here is that we cannot necessarily, we cannot guarantee generalization properties, but there are promising avenues that we can follow that would help us ensure these generalization properties to a certain extent. And that is really the holy grail at the end of the day. So those are the two fronts that I think are very exciting and that are coming up from the deep learning domain.
Great, thank you, Amanda. Now I want to pivot to Maria, and in part inspired by the human in the picture that Rachid brought us a little while ago. And I'm gonna go off with some recent presentation that Maria, you gave in a recent AAAS meeting with the title "Robotics: Empowering and Not Replacing People." And there you highlighted the fact that it is, and this is true for any new technology, that essentially it eliminates some jobs, but at the same time it creates others, moving them from one economy sector into another. And some might argue that the two sides not always balance out, but that's a different discussion. What I would like you to give us your perspective on is, where do you think this employment give and take in the specific field of multi-robot systems is And what are, when we task swarms of drones in the sky or platoons of vehicles on the highways, what can we expect in terms of this give and take for jobs and human involvement?
Sure. Well, I mean, right now there are economics data that show that the introduction of robots kind of improves the economy because you have the ability to do tasks. Robots can work day and night. They have long turns and all those kind of things that we know about. I think also one thing to take into account, to remember, the robots have been introduced mostly to replace dangerous jobs. I don't think anybody today would think about having humans doing spray painting for cars or welding. So there is value because you save life for people that we're going to get sick or whatever from the job. So that's something to keep into account. I think the next frontier, by the way, I think is going to be agricultural applications. And if you think about, most of the jobs here are very low level, very dangerous, very tiring, and don't require much education. So the issue to me really is, yes, robotics is going to remove some jobs and produce other jobs. Now, is the world ready for those other jobs or not? And I think there are two things. First, as roboticists and designers, I think we have to make sure, robustness, reliability, scalability, all those things, ability to use simple interfaces have to be there, right? So this is our job. And if we don't do it, everybody else will suffer. But from the point of view of everybody in the world, and again, think about all the audience here, it means everybody needs more education. That's kind of the fundamental issue. The way of getting out, of a lot of situations with poverty, or again, these jobs that have absolutely no content, is education. And of course, education is not available everywhere in the world, right? Because not everybody can afford education. So again, it's very complex economic issues at the world level that have to be addressed. But I think as long as people push more education so they can be the people who repair the robots and fix the robots and get them to work. And they can also be creators, come up with new ideas, right? When things get used, people come up with new ways to do. Just a simple example, think about social networks. They were invented by computer scientists. Then they've been taken over by the world. And now they work differently. I'm not saying it's better, differently than the way they were designed. So again, we need this again, the creativity that all these new people are going to come and be educated in kind of science and robotics. They're going to add their creativity to the world. And we're going to create many, many more interesting things.
Great. So you brought up a couple of points that I just want to emphasize a little bit on. So one of them is creativity, new things popping up. And the other one is the issue of equity in relation to education and participation in the robotics revolution. Could you also talk to us a little bit about that other aspect that robotics can, as a field, as a technology can offer, which is being able to perform tasks, and to the degree that you're aware and you have experience in your own work, perform tasks that before they were just impossible to do.
Yeah, I mean, there are, one of the key things, for instance, people talk about is not working yet, is individualized delivery of products done by robots. I'm not sure that UAVs, and they will fly every morning in front of your house and drop your newspaper. I don't know they will be available, but there's a lot of other things in which, again, kind of improve the delivery. Think about how many people have to drive gigantic trucks across the United States, right? On big freeways. Maybe Europe doesn't have as many long, miles and miles and miles. Now, if we can reduce this kind of task, because there will be some automation, right? The trucks, at least on the freeways, maybe will be automated. Then the drivers will be able to do something else, right? So that's just one of the areas. And delivery of things, again, think about isolated areas where it's difficult to get things. But I think also, again, I really believe in the creativity of people when they're given the right tools. Again, think about the apps, right? since people started being able to write apps relatively simple, now there are lots of apps, right? I mean, I heard, for instance, apps that people use in Africa, so that women, when they have to get up at 4 a.m, they walk for miles to go to the job, they can connect with each other, so they don't work alone, right? Now, when people invented apps, nobody thought that this was going to be a good application. So I really believe in the intelligence of people and their ability to come up with creative solutions. And I think, to me, this is a very exciting part for the work that we're doing.
Yes, yes. You mentioned the adjacent possible that is being created with all this new technology. Yes, amazing. So I want to stay a little bit on the topic of humans and move on to Rachid. Rachid, you talked to us about robots operating with and around humans, right? A concept that appeals to me also, and links directly to some of my recent work. So, in the context of the theory of mind, what do you think that the robot thinks of me? And so, what is your perspective on robots building models on human mental states and intention? And how critical do you think this is in terms of reasoning about social or physical interaction between humans and robots, either in a collaboration or even in isolation?
Thank you, Bert, for this question. Yeah, I really think in human robot, at least face to face, I would say, collaboration or interaction, this issue of estimating of putting yourself in the shoes of the other, okay, is key, because it helps you to better interpret and understand what the other is doing, what the other is understanding of the task, how you can even speak to this person or point something or refer to something. You cannot refer to something that the other cannot see, for example, or not, at least not the same way. And so the first thing that we are trying to do when we build this kind of human-robot interactions is what we call the perspective taking, okay? Trying to already estimate, in a way, the perspective of the other. Okay? And we think that this level, and at least when you come to, I would say, to known tasks or to simple applications like fetch and carry, okay, or object manipulation, etc. I think it has its full. It is amenable. We can do it. Okay, it is possible to build it, and it could help a lot the robot when it has this ability. Of course, it is limited to these issues. The robot doesn't need to estimate all what you think about politics and other issues. It is simply linked to the task at hand, but already it could be very powerful and pertinent. By the way, by discussing this issue of perspective, I found out that basically, I don't know why, my background is inversed. I don't know if you see it. For me, AI of good is exactly a mirror issue.
Okay. Moving from one robot thinking about the world and humans to multiple robots now. When a robot swarm is to interact with humans, either one or multiple, to me, this seems to be an extremely complex, even possibly hopeless problem. How do you think that, what kind of coordination architecture, would it be hierarchical? Would it be reactive? How do you think we can start thinking about and organizing this chaos of potential interactions in this unpredictable and unknown setting?
Well, you are drawing the big figure, and it's true that when at this level, it is huge and it is very complex. But I think that first distribution is needed. The things should be done in a distributed way, because this helps to have. We'll come back to this issue of, I would say, robustness or ability to react to contingencies, etc., or to work locally. I think distribution is there and should be there and should be exploited. Sometimes there is also some kind of centralization, but the centralization will be essentially, I would say, on what I would call background knowledge. Okay, it's there that you will have the highest level of centralization. Okay, the background knowledge, the things that are shared a priori by the systems, not always, of course. Sometimes you can even increase this common ground, So I think we have to play and build with this issue of distribution and when needing local hierarchy, I would say, local centralization, only local, okay? And also playing with this issue of, I would say, background and general knowledge that is shared, okay, that is introduced and learned a priori and exploited and perhaps also improved or enriched incrementally. And the second aspect that we can, I would say, have to take into account and deal with is that we have to be modest, I would say, and think and instantiate the problems into specific, I would say, domains, for example, at least when we are today. But I really think that we should be able in I don't know when, but to reach at least a level when different systems can share space, for example, efficiently, okay, in a distributed way. For example, humans and robots, different robots from different companies, etc. So what is I would say implemented on the system? What is in the rules? Perhaps we can invent rules for sharing space that could be shared by all these systems. Okay, we have rules, for example, traffic rules between us, we humans. Okay, for example, and we can imagine to extend this to other situations.
Thank you, Rachid. So I take from the your original response that it's neither completely distributed, it's neither completely centralized. It's the right solution is probably somewhere in between, and it's up to us to figure out exactly where to put the slider.
Yeah, exactly. Very often we have both. We have distributed and we share global knowledge. Okay. Sometimes which will help us.
Right.
And we share global values also. Values, knowledge and values. I come back here to Maria discussion.
Yeah. Okay. So I have a couple of questions that I want to pitch to all of you, and whoever feels probably more stronger about it can start with a response. The first one is kind of I would say broad and kind of general, but I think it's important to lay out a little bit of structure and at least give our audience some idea what we mean by certain terms. So in our perspective, we talk of autonomy, the ability of systems to make decisions on their own, and we have artificial intelligence on the other side. Do we see autonomy as being part of AI, or AI being a key element of autonomous systems? Can the two coexist or exist in isolation? Can we have autonomy? Can we have autonomy without intelligence, and vice versa? What do you guys think?
Well, I mean, I think autonomy is always, I mean, if you think about AI tries to make a system that makes decisions, right? So autonomy is kind of the core of AI. Now, whether we want to start thinking about slightly differently, that's one way of looking at it. But I'm not sure without AI, I mean, you can have fixed autonomy, in the sense that you have fixed rules, right, that you give to your robots, and then they follow those. I don't call that real autonomy. I mean, they do things on their own, but they are rigid. Now, a lot of the system we talk about have some kind of learning or have things ability to adapt to the environment, and that's, to me, is the more important view of autonomy. You are autonomous because you can adapt, make decisions, but adapted to the current situation.
Okay.
Yeah.
All right. So, in your view, Maria, autonomy should be somehow linked to adaptability. I would also go one step further, and that's probably a pass to Amanda, and possibly resiliency. Being able to figure out responses to unanticipated situations, right? So not everything that is already scripted in some manner or form or code or algorithm, right? It was already your response, Maria, was already a pass to Amanda, and maybe Amanda is probably better suited to respond to my next question, which is because she talked about scaling up and scalability. So artificial intelligence for multi-robot systems, do we feel is a primarily a matter of scale, or are there other problems that are linked to the possibility of using AI for multi-robots? We're not talking about a single robot, a single system, but a collection of robots interacting with each other.
So your question is what are further uses of AI?
So my question is whether implementing AI, however everyone feels about it and thinks about it, to multi-robot systems, whether we think that the major challenge in doing so is scale and computational complexity, or are there other very important issues that need to be also brought in the forefront and dealt with?
So that is a really interesting question. So it's true that as we think about training algorithms, so a data-driven method for multi-agent or multi-robot systems, the efficiency of these training algorithms tend to be quite low, because as you think about, if you take a step back and you think about the numbers of examples that a single robot needs to see in a single robot environment, it's typically smaller than the numbers of examples a multi-robot team needs to see because of the combinatorics of the multi-robot system state. So I hope my audience is following me. So obviously, if you have a larger team of robots, there are many more configurations that this larger team of robots can be in. And all of those different configurations have to be fed to the team as they learn how to deal with these different situations. And so what this basically boils down to is we need much more data and much more time in order to train an algorithm that can do something relatively simple. I think time is a problem. Simulation doesn't come for free. And actually in my lab, we've been starting to think a little bit more about the environmental impact of all the training that we're actually doing. So we're actually using a lot of energy in order to train a couple of these policies, and we don't take this lightly. And so we've been taking a step back and trying to think about, okay, what is it that we can do in order to make the training of our algorithms more efficient? One, simply by developing better algorithms, but two, we're trying to build models, freeze them, and try to understand how we can use already existing models that are potentially flexible in some way, and that it can be reused for other tasks without having to retrain like building blocks of models again. In a sense, trying to not like saving that amount of training that we invested in training those component models. So that's kind of a side note, but I think it's important to mention that AI is good, but it doesn't come for free. And thinking of scalability. So as we create larger systems, as we create more complex environments, that implicitly means we need more data, because we are implicitly talking about more things that the robots have to learn how to deal with. And there's no free lunch when we're using a data-driven approach, because it comes through data, and data does actually also mean time in many of these cases.
Yeah, I have a comment to add.
Of course.
I think that the scaling can go in two ways somehow. You have the numbers, the number of agents, a lot of agents, okay, but you have also something you spoke about, autonomy, which is scaling in the variability of the situations that the agent has to face. Okay, even if it is alone, I would say, or there are only two or three. Okay. And autonomy goes for this. AI needs also for this, the ability to deal with a large variety of situations. Okay. And so the scaling goes in these two directions. And now now if you go to multi-robot, I think multi-robot is also interesting. I'm coming from multi-robot and went to human-robot collaboration because I feel it quite close, I would say, because we need also to understand, to design, to understand, to better understand what is cooperation, what is coexistence, what is between agents, what is sharing resources, okay, what is facilitating the action of the other, even in a small number where a small number of agents are acting and reacting.
Yes, thank you, Rachid. And I also want to emphasize and underline one of the last comments made by Amanda, that basically AI is not for free, right? So there's energy involved there, and there has been some very recent studies that caught my attention that actually try to quantify this energy utilization just for learning. So it's something that as a community we haven't started thinking about it, but in terms of bringing energy into the picture, it should start. All of us should start thinking carefully about utilizing and training models, because all of these things really have an impact on the environment and energy utilization. Possibly as a wrap up for our own discussion here before we open the floor to questions from the audience, could we possibly come up with maybe 3 ideas of challenges, or most important challenges or priorities that you think our community, our robotic community, should try? Not robotic, let's narrow it down a little bit. Multi-robot community should address as priorities moving forward in order to make the maximum positive impact to the world. Whoever feels more strongly can jump in and share their thoughts.
So I'm going to say something because I wanted to jump in and sort of, this tied to AI. So I would say autonomy and AI is not the same, right? So Rachid kind of pointed this out. Robots actually have to live in the physical environment. That changes the game. AI is a tool, but it's not sort of the same thing. And part of the reason why it's not the same thing is that physicality and that embodiment. And I think, that is fun. So I think from a multi-robot perspective, right, that is something that we really have to take into account, especially because we're dealing with more than one. And not only do they have to interact with one another, but they have to interact with the environment as well as any other actors within that environment as well. And I think one of the big challenges sort of moving forward right now is really just thinking about how can we leverage this ability to be able to do large scale, at least in some of the problems we're thinking about, large scale sampling. How can we use these tools to help us collect data, but really reveal things about the natural world that we don't know, right? So this is about discovering new physics and getting new physical insights into the complexities of the systems around us that we interact every day with.
Thank you, Annie. Now, there are probably multiple challenges involved in what you just pitched to us. So, but I'm going to pretend that this was just one direction that we should definitely put some time and attention to. Any other ideas about priorities for our community, our collective robotics, multi-robot systems? Some topics that we really need to pay attention to. Rachid is.
I would think that perhaps I said it before, but I really think that we all know that in the future a robot will never be alone. Okay, very rare. Okay, perhaps in the moon or in Mars, but for the rest, and even there now there are several. Okay, the robots will never be alone, and in what they are. And so I think one key aspect is really to equip the robots with the ability to share space. Correctly. I mean moving robot, of course, share space with humans or with other robots from other companies, etc., while performing their tasks, of course. So it's kind of generic ability that is integrated in these systems. And it's not clear how it can separate it, because very often what I see is that they are very often put together, and it's not that clear. And I think it's a real challenge. Okay, of course, in the generic way. Okay, real environment, physical space, real robots, big and small, walking and driving, flying, everything.
Okay, thank you, Rachid.
Can I add maybe quickly?
Of course.
A challenge which is not just for robotics. I mean, here I talk about AI for good in this group, and I really want to think about a broader picture here. So what are the challenges? First, we have to make sure that, again, the AI does something good for humanity, not just for the rich or for the few who can afford it. We have to make sure AI, there was a discussion in the chat, the decision made by system can be interpreted, they are fair, they are unbiased, and everybody's access to this technology. I think, again, fundamentally, that's a message, this is a technology for everybody, not just for the few privileged. And we have to figure out how to make everybody capable and able to access and to use these technologies well developed.
Yeah,
I have to say, I fully agree.
Yeah, all right. So I know that we were given a little bit of extra time to our session by the organizers, but I want to jump off to some of the questions that we received in the chat and just bring it up to all the panelists, starting from some of the early ones that we received. And one is about the role of designers in the future of HRI standing for human-robot interaction. And that's probably a question to Rachid and Maria in this context.
Yeah. Well, I tried to answer very, very quickly in the already there. I think, yes, it is important. It is absolutely important today. It is starting. We are collaborating with some colleague designers to have, I mean, at scientific level, but also in building a system to enrich our collaboration with designers. Co-design is a key aspect. Co-design also with users, okay, directly with users, of better if they are coached, I would say, and helped by designers and the people who are who are educated and who know how to design things. It's a key aspect, and I think it can be studied at very generic level, but also and more I would say efficiently in application when building one given system.
Okay. Another question that we received is about using neural networks as a black box. I mean, this is a, and I'm not saying that we necessarily use them in that way, but they have been traditionally been used as black boxes. In this way, could it be difficult when someone is trying to ensure that the systems operate safely or efficiently? I mean, how do we get guarantees when any sort of performance or safety guarantees by using neural networks as a black box without understanding really what goes under the hood, goes on under the hood?
Yeah, I think is a big problem. I don't want to take much time. I think it's, as a AI community, as researchers, we have to kind of address, we kind of created something that now can make decisions for us, and we don't know exactly how the decisions are made, right? We are not 100% sure they are correct. Think again about the generative system like for language, which is always a good example, right? So I think we have, as a community of AI researchers, sort these things out before we look at the implication for robotics. It's a big problem, it's a big issue. I'm sure it will be addressed, but exactly how, I don't know.
But so I think this is this new area, right? So there is a sort of safe autonomy, safe AI, and it is this emerging area in research, right? And there are people that are starting to look into this, and how can we think about doing learning, but with performance guarantees and understanding the limitations of what we learn.
But I think there is another level, which is I think it is important in the future to equip the robot with the ability to permanently, globally assess themselves, their performance. Okay, so it's more than assessing one algorithm, but assess the performance of one algorithm. Okay, but assessing the performance, how good I am. Okay, and we have started some work here. We call it in human-robot interaction, the robot trying to estimate the quality of interaction. It's not enough to adapt, because you could adapt and adapt and adapt, and doing so you harass the person by adapting and readapting. Okay, it is important to assess globally the quality of what happens, the pertinence somehow. I think one key word could be the pertinence, the ability for the robot to ensure that it is pertinent somehow, and then take measures if it's not.
Okay, I want to save a little, maybe our last couple of minutes here to another question from the audience that touches upon the issue of the role of information in decision making. And I'm going to interpret a little bit this question as when talking of information, I would get out on the lip here and say that this is particularly important for new information, and it touches on some of the issues that Annie was talking late in her talk about sensing the environment and utilizing information, distributed information into and improving the model that goes back and drives further decision making and data sampling. So new information, real-time information, and its role to decision making. How do we see this loop, this circle, this cycle of sampling, decision making, control, and intelligence in there? Information to drive sensing and decision making to drive further information collection.
So I guess I will step in. I think this is, I think like humans, right? We kind of have a prior model of what's going on. We interact with our environment. We sort of assess what the situation is. We update or not update that model. We make a decision about that. And I think that's essentially what we really want our robots to be out there doing, right? So nothing, this idea of the adaptations, this idea of being able to adjust, right? It is this idea that you can, in fact, assimilate new information, somehow be able to reason about, compare that new information and assimilate that into sort of your existing corpus of knowledge, right? And be able to, update your information, update your decision making based on that. And I think that is essentially what we would like our systems to be able to do.
Thank you, Annie.
Yeah. Right.
Yeah, Rachid, do you have?
I think that, yeah, I think again for the information, it goes. It is quite large concept, because when you see the robot, what kind of it has, it receives information somehow. What is the information it is able to use to effectively perform?
That's another.
Its task, and also to be sure, and we have to ensure that it is extracting enough information and the pertinent information to achieve its task. Very often this is forgotten, because very often the engineer is looking for optimality. Okay, and when doing this, we lose something, as Amanda summarized before. Okay, etc. And we discussed also Bert a little.
Okay, I think that should wrap things up. I want to thank you so very warmly, all of you, for sharing your thoughts and your views and your mind with us today. Also thank the audience for participating in this and sharing questions with us. And I'm going to pass it back to Guillem.
Thank you.
Session.
Thank you very much, Bert. And a big thanks to all our speakers today, Annie, Amanda, Maria, and Rachid, as well as to all the participants for making it such an interesting discussion. We now encourage you to check out the AI for Good program online to see more robotic sessions that may be of interest to you starting from January 2023. And we would like once again to thank you very much, to thank you for joining us today, and looking forward to welcoming you on board again at AI for Good soon. Thank you very much.
Thank you, Guillem.
Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.